So I did it to because David White, who started talking also about the homotopy theory of ideals, the stable homotopy.
Great, yeah, thank you so much. Just wanted to say thanks to the organizers for putting on a conference session in amazing place, and thanks to all of you for coming for the last talk, first day here. So everything I'm going to say today is joint with Donald Yau of Ohio State Newark, and I put the slides on my webpage, and then I put a tiny URL over here just in case you decide midway through the talk if you want to get them. This is, I think, the biggest you're actually allowed to write a tiny URL, with as much space as possible on the board. The story here is that the concept of an ideal in spectra was proposed by Jeff Smith in a talk in 2006, but then he didn't write up the corresponding paper explaining what it was or how to do what he had said was true. So Bob Bruner and Dan Isaacson took notes during this talk and gave them to my advisor, Mark Hovey, and he wrote up a preprint about it, but then he too stopped doing research mathematics. So I saw a way to generalize what he did and finally get these ideas actually published. And so I'll tell you a bit about what we're going to do today. So I'll explain a bit about just the whole overall idea of brave new algebra, and then I'll tell you what Jeff Smith said an ideal should be, and also the connection to algebraic K-theory. And then I'll show you how to do it not only in the category of spectra, but in any nice stable monoidal model category. And then kind of my part with Donald Yau is to extend this notion to structured ring spectra or structured ideals, structured by any operator. But if you don't like model categories, that's fine. You can just follow the whole talk thinking of M as either symmetric spectra or thinking of it as chain complexes over ring if you're more into homological algebra, or the stable module category if you're more into representation theory. So this talk works in any of those settings. And it also works in an infinity category context if that's your preference. And at the end of the talk, I'll give you lots and lots of open problems, because the whole point of doing this, finally writing this up, was so that people could actually start to then work with these ideals of ring spectra. So hopefully there's something there for the grad students who are interested in finding stuff to do. And of course, I have to thank my advisor, Mark Hovey, for giving me his preprint, and also Bob Bruner and Dan Isaacson, who took those notes in 2006 and then shared them with Mark. Okay, so what is brave new algebra? This is something that we like to talk about in stable homotopy theory. It's kind of an analogy between stable homotopy theory and classical algebra. So instead of the ring of integers, we work with the sphere spectrum. Instead of abelian groups, we work with S modules, which are spectra. We can talk about ring spectrums, ring spectra. Instead of commutative rings, we can talk about E-infinity ring spectra, or strictly commutative ring spectra if you like. And there are notions of things like projective modules, injective modules, homological dimension, the notion of a semi-simple ring spectrum. Lots of things from algebra have been brought over, but the notion of an ideal had not been brought over until Jeff Smith proposed a way to do it. So there's a few problems with trying to kind of naively do it. I mean, what is an ideal classically? I have an element of I times an element of R goes back into I, but we don't have elements when we're working in spectra, so that's not a good definition. And you might say, well, okay, maybe it should be a subobject, but that's not a great idea either, because in homotopy theory, every map is homotopic to an inclusion. So subobjects are not a great idea. A better idea is, an ideal is something I can quotient by and get a rating on the other side. So an ideal is something where, R mod I should be a ring spectrum again, or a ring object in these other algebraic settings. And so that was what Jeff Smith proposed. An ideal should be an arrow, J, with extra structure. I'll tell you what that structure is on the next slide. So specifically, if we have a closed symmetric monoidal category, so it could be the category of, say, symmetric spectra, or it could be chain complexes over a commutative ring, or it could be the stable module category, then the arrow category, the category of morphisms, has two monoidal structures. It's got a pointwise tensor monoidal structure, where you just take two maps and tensor them together pointwise, and it's got the push-up product monoidal structure, where you take two maps and then you kind of write down the square that they form and the push-out product corner map. And what Jeff Smith proposed was that an ideal should be a monoid with respect to this second structure, with respect to this push-out product structure. And notice that a monoid with respect to the first structure is actually just a monoid homomorphism. If I have a way to go from F tensor F to F, then that's going to end up telling me that it's a monoid homomorphism. So let's unpack on the next slide. What is this? What does it mean to be a monoid with respect to this weird push-off product function? And why is that a good idea? And then we'll work out the homotopy theory of these things, and then I'll give you some open problems. So, well, all right, so what is a Smith ideal? It's a map. And it turns out that the codomain is a monoid. The domain is an R bimodule, and it's a map of R bimodules, such that you can multiply on either side and get the same answer. So one way to say it is it's a central R bind, central R bimodule. And to figure out why the definition unpacks to that, the unit of a Smith ideal would go from the unit of that push-off product monoidal structure into the map. So that's going to give you the unit on the codomain R. And then you've also got the multiplication. So the multiplication says, I've got a way to get from the push-off product of J with itself to J. So this vertical map here is J box J. And, oh, sorry, no, this map is J box J and this map is J. So, and the vertical map here is this mu. So when you unpack what that means, it's telling you that the codomain is a ring object. And it's giving you the central bimodule structure with this one. And the upshot is that when you have one of these Smith ideals, if you take the co-kernel of this of the map J, you get a monoid homomorphism. So R mod I is a monoid or a ring object, and the co-kernel is actually a homomorphism. So that's easy enough to see because the co-kernel can be thought of as a push-out, and this push-out product is also a push-out, and push-outs can be with each other. So in Hovey's preprint, what he wrote up is that this co-kernel functor is actually strong symmetric monoidal. So, you know, from the push-out product monoidal structure to the pointwise monoidal structure. So therefore it lifts to monoids, and that gives us a way to get from any Smith ideal to a monoid homomorphism. And in fact, that's equivalence. That was Hovey's theorem. So to prove that, you really do need the stable structure on M. It wouldn't work for, say, topological spaces. It has to be spectra or chain complexes for the stable module category, because you're going to use co-fiber and fiber sequences to compare kernel and co-kernel. So that's all in Hovey's preprint. Oh, and by the way, the last slide of the talk will be references. So you can get papers from archive or wherever at the end. So let's unpack this thing specifically in these algebraic contexts. I wasn't sure exactly what the audience would look like. So in representation theory, you can start with a field K and a finite group G, and you can do modular representation theory studying it via the stable module category, which is a stable model category, and it's a monoidal one as well. And so a monoid is an R algebra, and a Smith ideal is a central R bimodule, specifically. So when you take the image of such a thing, you get an ideal of the codomain. So that's what we recover the old notion by ideal. And then in homological algebra, if you have, you know, if R is a commutative ring, we could look at the chain complex, which is R in degree 0 and 0 everywhere else. And you can consider what's an ideal of that thing. And it turns out that an ideal of that thing, again, just yields an ideal of R. So that's good. But you can also look at, you know, monoid objects in chain R, and they are differential graded algebras. So then you can ask, well, what's an ideal of differential graded algebra? It's going to unpack to a homogeneous ideal. So that's good. We're kind of recovering classical notions. But for ring spectra, it wasn't known what it was. And so what's it good for? I mean, why is this the right definition for ring spectra? I mean, one thing is we can quotient out these, so that's good. But it also has a nice application to algebraic K theory. So suppose I have a spectrum with two different Smith ideals, and there's a pretty obvious way to temper them together, because you just have a map from I to R and a map from J to R, and so you've got R tensor R, that goes furthermore to R. And suppose we compute the following homotopy pushout in the category of associative algebras, or in the category of monoids. Then what Jeff Smith realized is that there's actually a fiber sequence in algebraic K theory relating the algebraic K theory of R quotient by this ideal, and the algebraic K theory of these two objects, and the algebraic K theory of T. Without this push out. So this is cool. This is a way to potentially get at things like the algebraic K theory of Z mod 4 or something from simpler pieces. So that's where, you know, Smith left. He basically gave this talk in 2006 and said, this is what an ideal is, and here's what it's good for. And then, you know, people were left to wonder if that could be worked out. So this this part of Smith's vision was proven by Land and Tama only in 2023. So they had a wonderful paper in 2019, an Annals paper about pullbacks in algebraic K-theory, and they introduced this kind of mysterious circle dot product. And then in 2023, they came and worked out push-outs in algebraic K-theory, and it turns out that this T, which can be computed rather simply as this push-out in in just monoids, turns out to be a way of computing this circle dot product. So suddenly, Jeff Smith's thoughts from 2006 are looking a lot more relevant. It's a way to get at this mysterious circle dot product. And furthermore, in the paper of Land and Tama, they talk about if everything in sight is, say, has an infinity structure, and that's an important way that they can get a handle on their computations. In particular, if you want to have any hope at all of this circle dot product being commutative, you definitely need everything to be infinity plus more. They talk about in the paper how to make that happen. So that gives some motivation of why you might care about E infinity ideals instead of just monoids in the arrow category. Maybe we want R mod I to be not only a ring spectrum, but also a structured ring spectrum, like an E infinity ring spectrum. So that was part of the motivation. Okay, so with Donald Yau, we realized that we can actually encode this notion of a Smith ideal as an algebra over a two-color. So that allows us to generalize from doing everything in terms of monoids in the arrow category to doing O algebras in the arrow category for any operator O. If you don't like operators, you can just think about it as saying, hey, now we can do commutative monoids, or we can do A infinity or E infinity, or whichever ones you like. So the point is that we want the co-kernel to be an O algebra morphism, and then we work at the homotopy theory of these Smith O ideals. So there's two ways to lift an operad to the arrow category. You can either lift it using the pointwise nodal structure or using the push-out product nodal structure, and that gives us two different operads, which we denote like this with the circle times where the dot or the box. And a Smith O ideal is an algebra over this box one, just like before it was a monoid in the push-out product nodal structure. And a morphism of O algebras is an algebra over the other way to lift the operad. And the good news is that Hovey's theorem goes through. So we now get equivalent equivalence between Smith O ideals here and O algebra morphisms here. So that's good. And I mean, I don't want to get too much into the weeds of how we did that. So I'm not really going to talk about the model structures in this case. I'll just point out for experts, to make this monodal structure play nicely with the homotopy theory, you use the injective model structure. And to make this one play nicely, you have to use the projective model structure. And it's really not hard to lift operand algebra theory to the injective model structure, but it is hard to lift it to the projective model structure. We've lost control of the co-vibration. So we have a trick to get around that. We wrote down a two-colored operand that encodes what it means to be a Smith O ideal. And I'll tell you a little bit more about that in a second. So what is a Smith O ideal? Well, again, the motivation here is that it's a map, and it should be a map such that the quotient is now an O. That's what we're looking for. So in particular, the codomain is an O algebra. The domain is an A bimodule. The map itself is a bimodule map, and there's this kind of centrality condition that says, if you start with something that has a bunch of copies of the algebra and two copies of the bimodule, then you can multiply them out. Either you can use the operand, the Smith O ideal structure in either order, and you'll get to the same answer at the end. So that's kind of the centrality condition. And again, I wasn't quite sure what the audience would look like, so I put this slide up, but I might quick step past it. But this is the way to get at what is a Smith O ideal in terms of this two-colored operand. So this two-colored operand has two colors, one of which is for the codomain, giving you a way to multiply it together, and the other one is for the A bimodule structure. So that's kind of nifty. Cool, so that's what a Smith O ideal is. And then what's the homotopy theory of them? So it turns out, just like Hovey proved, we're able to prove that for any kind of reasonable, and I'll talk more about what I mean by nice here, for any reasonable, stable monoidal model category, like symmetric spectra or chain complexes, or the stable module category, there is equivalent equivalence. So the homotopy theory of Smith O ideals is the same as the homotopy theory of O algebra. There's a way to get between them. which is great, because that means if you have a Smith O ideal and you take that quotient, you do get an O algebra on the structure on the quotient. So that in particular, if you're doing the non-common thing, you have, say, R mod I is an E-infinity ring spectrum. So that's good. You have some hope to kind of apply that machine. So again, I don't want to get bogged down in the details of the model structure, but the point is that how nice you need the model structure to be depends on your infinity or A infinity. Then you don't need much at all on M. In fact, it's enough if M is just any old stable monoidal cofibrantly generated category. So, you know, if you come across them in the wild, you can use this theory on sigma cofibrant operands. But if you want to use it on strict commutative monoids, then your M has to be a little bit nicer. It has to satisfy this strong commutative monoid axiom from my thesis. And if you wanted to work for a general operator with no covariancy on O at all, then you basically need to know that these functors are homotopically well behaved. So doing things like taking a big push-up product of trivial cofibrations, and then quotienting out by the sigma n action, the symmetric group action would still give you a trivial cofibration or something. So you might say, well, that condition seems really strong, but actually that condition is satisfied in most of the examples you come across. So it's satisfied for this is the strongest possible condition, meaning this theory works for any operato, any colored operato, holds for symmetric spectra or equivariant orthogonal spectra or motivic spectra if you use these positive flat model structures. It holds for chain complexes over a field of characteristic 0. But if you drop the characteristic 0 assumption, then this story only works for sigma cofibrant operands. There are counterexamples. And the best possible scenario works for the stable module category as well. So I've written a bunch of papers with Donald Yau. We like the stable module category because it's a fun example of a model category. And we were not aware of anybody else ever having done operand algebras in that context. I don't know why. So we wrote it up in one of our papers. We talk about like, what is an E-infinity algebra here? And do I have rectification, things like this. And if you're aware of other papers that talk about operand algebras in stable module category, please let me know. We should have cited them, but we couldn't find them. I was kind of amazed that nobody ever talked about them. Because it is a nice monoidal structure, so you could talk about algebras. Okay, so that was our kind of first main result. And then, so now we know what the homotopy theory of Smith O ideals is. But the second main result that we proved was a comparison to the infinity categorical way of doing things, because some people don't like model categories, they want to work with infinity categories. So basically, if you want to get at the homotopy theory of Smith O ideals, or in general, any operand algebras, you've got two ways to go. You can start with your model category M, and you can transfer a model structure or a semi-model structure up to O algebras, and then you can pass the associated infinity category. Or you could start with M, path to its associated infinity category, and then look at algebras over the associated infinity operand. Do you get the same thing? That's a pretty natural question. The answer is yes, you do, if the operator you started with is sigma cofibrant. But it's not true in general, by the way. It's not true, for example, if you start with topological spaces or simplicial sets, and if you start with O being strict commutative monoids, you will have to get two different answers by doing this these two ways around. So you really need this sigma cofibrancy. So we proved this result, and I could go into more technicalities, but since it's a short talk, I won't. I mean, we needed to use Gruner-Haux's theory of what it means to have a subcategory of flat objects, and we kind of relied on a lot of just work that Hauxing had done, kind of understanding the infinity operand side of the story. All right, so now we pretty well know what the homotopy theory of these Smith O ideals is. So, what's it good for? Like, what are some more questions we could ask? Basically, I felt like at this point we'd written up what Jeff Smith said was going to be true and what Mark Hovey wrote out, and then we also did it for any operator instead of just associative algebras. So here are a bunch of open questions that might be interesting, and many of them are open because not necessarily because they're hard, just because they haven't necessarily nobody's tried them. So, if we start with a ring spectrum, we can take its homotopy, we get a ring. That thing has ideals. What is the relationship between those ideals in the homotopy world and the ideals of ring spectra? You could ask the same question in the stable module category or chain complexes. But here's the simplest example, possible situation, and already the answer is not so clear. if we start with the sphere spectrum, we take its homotopy, so we're looking at stable homotopy. There's an ideal generated by 2. But if you try to think, how do I lift that ideal to the level of spectra, you might come up with the mod 2 more spectrum. That's usually what we do when we want to invert, generate by 2. But that's not a ring spectrum. So that's the wrong way to lift it. So already a basic question that we don't know the answer to is, what is the ring spectrum quotient of the sphere spectrum by the times 2 now? Because it's not the thing that, it's not the mod 2 more spectrum. It's supposed to be we're supposed to get a ring spectrum. Another open question is every ring spectrum is actually weakly equivalent to a quotient of the sphere spectrum. Why? Suppose I start with a ring spectrum, then I've got the unit map from the sphere into it. That's a ring spectrum morphism. So you can take the kernel of that, and that's an ideal because of the Hovey's theorem. And if you point it out by that, you have the ring that you started with. So your ring is definitely a quotient of the sphere spectrum. Hovey proposed a notion of what it might mean to be a strong quotient. So a natural question would be to try to classify those. This was a question that Hovey posed in his preprint, or to relate this notion of a strong quotient with the notion of a Smith ideal. Another question is Matan Prasma came up with the notion of homotopy normal maps to try to generalize the notion of a normal subgroup and bring that to the level of ring spectra. So you should kind of get the same theory with ideals of rings versus normal subgroups of a group, but nobody's worked out that connection. Not necessarily because it's hard, just because nobody has tried to do it. I've got more open questions. So what's the Smith ideal generated by something, right? I mean, normally if we have an element, we can generate an ideal by it. You might think, well, I'll just, so I start with a map, I'll just apply the free monoid functor, but then the codomain would no longer be R, would be T of R. So you'd have an ideal of the wrong ring system. So how do you get it back to R? You can ask questions, what's a principal ideal? What's a maximal ideal? Can I do regular sequences? Can I do Krull dimension? All the questions from algebra are now open to you. Now we have a notion of an ideal. So I encourage you to do it, and I'm happy to talk about it. We've still got several days left of the conference. My own thoughts on these things. You can also try to do a non-commutative version with left and right ideals. The reason for the centrality is really because we're dealing with a symmetric monodal structure, but you could look at homotopy theories where you don't have a symmetric monodal structure, and then you could look at left and right ideals. And then in the paper, which is published in AGT, we list a whole bunch of conjecture problems in section 6. So all sorts of things about how can I, get a better handle over this theory in other contexts. So if you like model categories, there's a bunch of open problems there. Okay. And there's also open problems relating to algebraic K theory. So, now that we know that Smith's vision is true, it's a great time to actually start computing these R mod I. Maybe you can start with S mod 2, that's a basic one to start with. And actually come up with models for this circle dot product based on ideals, and then use the fiber sequence in algebraic K theory to do new computations probably in algebraic K theory. Another thing you can do is Lambda and Tama actually don't only work with algebraic K theory, they work with a general localizing invariant. So they talk about how their theory also works for like wall housing K theory, and works for Dan Bergelia's work on periodic cyclic homology. But Smith didn't say that his Smith ideal should be useful in those contexts. He focused on algebraic K theory, so you could try to make the same proof work to get fiber sequences relating to these more general localizing invariants. Then you'd have a way to compute the Bergelia type periodic cyclic homology of some kind of push out using these ideals. Maybe it could work. Another point is that Lambda and Tama is really only about ring spectra. It's about symmetric spectra. But this work works in general stable model categories. So it's really well set up if you want to jump into a motivic analog of it, or an equivariant spectra analog, or chain complexes for the stable module category. I mean, this work that we did was in a much more general setting. So you could try to then go and prove, Jeff Smith's vision in those settings for any, localizing invariant in those different places. And then do some computations using them. So certainly encourage you to do all that. And if some enterprising grad student does want to pick up one of these things and do it as an exercise, I will just encourage you to submit it to the graduate journal in math, which is a relatively new journal that I'm on the editorial board of. So, there's plenty of journals for undergraduate math, but there was none for grad students. So this journal publishes, kind of interesting mathematics that a grad student might do. Maybe you work out a new example of something, or you give a new proof of an old theorem using modern machinery, or you work out, hey, what's a principal ideal? And turn out it wasn't that hard, but I still want to write it up and get it published somewhere. There's a good journal for you. Or if it turns out it's super hard, then you can publish it in Annals. All right, so that's the end of the talk. And yeah, thank you very much for your attention. I thought 13 was a good lucky number of open problems.
Right. Does anybody have any questions?
You back there?
So I have a question. So one is, you mentioned the example when you're trying from something equal, and then realize it in the respectable. So, I mean, there are these classical examples where you take a complex coordinate and you kill some regular sequences in there and get some of these truncated parameters and I don't know, like just lots or something like this. Is it known that you can do this on the spectral level using single ideas?
No, it's a great question, really great question, and it's not known. And the reason it's not known is not necessarily because it's hard, it's because nobody has tried. That's
I
kind
mean,
of
I'm getting something you want as well, because I mean, I was supposed to look at any dream about utility, it's working in the world.
right. No, but I mean, really, no. The entire list of papers that have been published about Smith ideals is my paper with Donald, and it appears as one line in the Lantan paper. So
And the related question also is that like, there is this construction, you can take an element of homotopic group of the reach spectrum, and then make the universal, say, EA quotient. You can kill it as a EA.
yes,
So I'm wondering if what you're actually doing is you're generating some EAs in that deal. So
yeah. So that one actually did work out, and on my computer I have the name of the paper, an early paper that did exactly that. And I went through that paper and I checked, and what it is doing is exactly a Smith ideal quotient. So that one I did work out, but it's not written down.
So in the local mood spectrum case, you are actually going to get the, say, quotient was used spectrum by, first, you need to generate some ideal legs.
Yeah,
And the state in the other,
right, yeah.
like,
When you have an orthogonal spectrum or symmetric spectrum, then you have ring of units for that spectrum. I was wondering about these topological models of units fit into quadratics, because if you have these ideals here.
Yeah, again, that's a great question. I don't know, I never thought. I encourage you to do it. We can talk more about it. We got several more days. But yeah, more now is 14 or 15 open problems.
So if you take quotients, if you take cofinders, so the infinity rings, I mean, often the cofinder, like, well, usually there's no algebraic structure. But there is obstruction theoretic methods for showing that sometimes the cofinders still E2 ring or E3 or somewhere between E1 or A1, E infinity. And is there somehow be able to see this type of obstruction theory with the Smith ideals?
I'm not really aware of it. I mean, the only paper I know is the one Irakli was talking about, who's I forgot the name of the author. But when I gave this talk, I talked like this at Loyola, somebody raised this point, and I went through that paper carefully. And in that case, the obstruction theory kind of works out. But yeah, maybe we should talk more after.
I was looking about like Hovey Barton, like actually covering paper, like the
I think it was, no, the one I think was earlier.
oh, yes.
Yeah, it was just like, right, EN, quotients of EN things.
Oh,
Yeah. So I don't know about this obstruction theory, but it's a good question. I think David had a question.
So you mentioned equivariant spectrum. Do you think that it works in infinity case or in E infinity case?
Right, so, equivariant orthogonal spectra with the positive flat model structure satisfies these conditions here, so that algebras over any operand whatsoever have a transfer model structure. and you've got rectification and all the nice things. Now, you do need this condition about cofibrant, basically cofibrant algebras for getting to underlying cofibrant objects. And that is true for, the infinity ones, right? Because they're cofibrant replacements and things. So I think I worked that out in my paper with Hovey and Gutierrez. This story should work for any infinity opera. I think so. Yeah, and also, yeah. I think so.
And would be rude to just ask a second, bottom spectrum?
Yeah, so I don't think it's ideals in the same context. I've never done anything with this, tensor triangulated or Balmer spectrum, but I mean, I don't expect any kind of connection. But then again, we don't even have a notion of a prime ideal for this notion of ideal. You think it would be related to the Balmer spectrum? I don't know. I mean, it's worth checking, but I mean, we're already stuck at problem 1 here, which is the relationship between ideals and the homotopic. Yeah, so I mean, maybe in the best possible world, but I wouldn't expect that nice connection. I think the Balmer spectrum is getting at ideals in a different way than this. But yeah, we should talk about it this week, maybe. I mean, like I don't know, for example, if you take an ideal in the Balmer sense and you quotient by it, you still get a ring structure, for example. Any more questions? If not, that's really good. Oh, I have